Have you ever stared at a big exam question and just had no idea where to even begin? Well, today we're going to tackle that feeling. We're breaking down a classic GCSE chemistry question about chemical cells, step by step. And we'll be using the official mark scheme to see exactly what the examiners are looking for. Let's dive in. So here's our game plan. We'll start by making sure we understand the experiment itself. Then we'll walk through each part of the question one by one, from control variables to reactivity, and we'll even finish up with a cool real-world example about hydrogen fuel cells. All right, first things first. Before we can answer anything, we've got to understand what was actually done in the investigation. Let's set the scene. Okay, so here's the setup they used. It's a pretty standard chemical cell. You've got two different metal electrodes sticking into a solution, which is our electrolyte. One electrode is always copper. That's our constant, our reference point. The other one, labeled electrode X, is the one they're going to change. And the whole thing is hooked up to a voltmeter, which, you guessed it, measures the voltage. The method is super simple, really. You just stick a metal in for electrode X, let's say you start with cobalt, and you write down the voltage. Then you swap it out for a different metal, and you do the exact same thing again. This simple process is what gave them all the data we're about to look at. And here are the results. Now, this is where it gets interesting. Take a look at these numbers. First, notice that when you pair copper with itself, you get 0 volts. That makes perfect sense, right? It's our baseline. But then look at magnesium. It gives a massive positive voltage of 2.71. And on the flip side, you've got silver, which actually gives a negative voltage. These numbers are the key to unlocking everything else. Okay, let's get into the first actual question. This is all about good science, making sure the experiment is a fair test. And how do we do that? By controlling the variables. So the question is asking for two things that had to be kept exactly the same for every single metal they tested. What do you think? What could affect the voltage besides the type of metal? So here's the list of possible answers right from the mark scheme. You only needed to give two of them. Things like the temperature or the concentration of the solution are really important because they can change how fast the reaction happens. But it's also about the physical setup, the size of the metal strips, or how far apart they are. If you change any of these, you won't know if the new voltage is because of the new metal or because you changed the setup. All right, now for the big one. This next part is worth 4 marks, which is a huge chunk. And there are 2 parts to it. First, you have to use the data to put the metals in order of reactivity. And then, this is the important bit. You have to explain how you figured it out. So, there's the task. Use that table of results to rank the metals from most reactive down to least reactive, and then justify your choices. Okay, if we go back to our data table, we can put this list together pretty easily. Magnesium is clearly at the top with that huge plus 2.71 volts. Then come cobalt, nickel, and tin, all with smaller positive voltages. Copper is our 0, and poor old silver is right at the bottom. So, there's our order. But how do we justify it for those extra marks? Here's the absolute key, and this is taken word for word from the mark scheme. The main principle is this. The bigger the voltage, the bigger the difference in reactivity between the two metals. And since magnesium gives the biggest positive voltage when it's paired with copper, it has to be the most reactive metal on the list. Simple as that. And this is the other side of the coin, which really seals the deal. The second justification point is all about silver. Why was its voltage negative? Well, it's because silver is actually less reactive than our reference metal, copper. That negative sign is a massive clue. It tells us the electrons are trying to flow in the opposite direction. So between the voltage value and the sign, you have everything you need to figure out the reactivity. Let's move on. Now that we understand that link between reactivity and voltage, we should be able to make some predictions. Let's see which pair of metals would give us the biggest bang for our buck. So the question is asking which pair would give the biggest voltage. Now, remember the rule we just established. The greatest voltage comes from the two metals that are furthest apart in reactivity. So looking at our options, which two have the biggest gap between them on that reactivity series we just made? And the correct answer is magnesium and tin. So why is that? Well, in all the pairs that include magnesium, we already know it's the most reactive metal. So all we have to do is find the least reactive metal it's paired with. And if you look at our list, tin is less reactive than cobalt. That means it's further away from magnesium, creating a bigger reactivity gap and a bigger voltage. All right, for the very last part of the question, we're going to switch gears. We're moving from a lab experiment to a real-world application, trains that run on hydrogen fuel cells. This is all about applying what you know to a new situation. This is a pretty fun question, actually. A newspaper called these high-tech hydrogen trains the new steam trains. Why on earth would they use an old-fashioned term like that? What's the connection? The whole reason is down to the chemistry. In a hydrogen fuel cell, hydrogen gas reacts with oxygen from the air. The only, and I mean only, product of that reaction is water. And because the fuel cell is hot, that water comes out as water vapor, which looks exactly like steam. So the steam coming out of this modern train is actually just clean water. Pretty cool, right? So we've broken down this entire question, from the experimental setup all the way to a real-world application. Now let's just step back for a second and think about the strategy here. So what's the big secret here? What's the key takeaway? With questions that give you a table of data, the trick isn't just knowing the chemistry. It's about being a data detective. All the clues you need are right there in front of you. When a question asks you to justify your answer, they want you to point directly to the evidence. Don't just say magnesium is the most reactive. Say it's the most reactive because it produced a voltage of plus 2.71 volts. Using the specific data they give you isn't just a good idea, it's how you get all the marks.